Registration that message have sent, no? Include the attendance. Yes. Fine, I didn't understood what.
Let's start here. So we can go one or two previous slides. So just for the sort of kind of a recap, one or two slides behind you can so shall we start now?
Yes.
Okay. All right. So let us continue from where we stopped last time, but I will take a few slides before to do a recap. We have been talking about how to analyze intrinsically disordered proteins, where the chemical shift dispersion is very poor, especially for the NH protons, but the N15 chemical shifts are very good, and therefore you create a three-dimensional spectrum where you have on two axes you have the N15 chemical shifts, and one axis you have the NH proton chemical shifts. And two particular experiments we considered, so-called HNN and HNCN, and these have different magnetization transfer pathways. And we also shown how these things can be analyzed. Sequential work can be done through this. In all of these, the glycine plays a very important role. I'm just saying in words what I already showed last time. The glycines play a very important role because they create a certain kind of a peak patterns in the various cross sections of the three-dimensional NMR spectra. So the so-called F1, F3 planes have direct display of the correlations. Will allow you to identify the N15 chemical shifts of residues I minus 1 and I plus 1 and the NH proton chemical shift of residue I. So sequential correlations are immediately seen. The corresponding orthogonal cross-section, which was the F2, F3 cross-section, again you see the same three correlations of a particular set of residues, I minus 1 and I plus 1, but this will be now displayed in the form of an HSQC. So therefore we call the F2, F3 as the triplet filter through the HSQC spectrum. So you got the NH proton chemical shifts and the N15 chemical shifts of the three consecutive residues, I minus 1 and I plus 1. And wherever there is a glycine, depending upon the location of the glycine in the triplet, whether it is at the I minus 1 position or the I position, it generates a different kind of a pattern of peaks. Pattern in the sense with regard to the signs of the peaks. And that is extremely useful, and that will allow you to identify where you are along the polypeptide chain. If you are walking through the polypeptide chain, you have certain patterns coming up one after the other, and that will allow you to, in fact, we showed here, for example, here we showed how you do a sequential walk through the HNN spectrum of FKBP. You have three consecutive, they're all F1, F3 planes. F1, F3 planes, you have a particular way to walk through. You walk through the chain in a sequential manner. You have the peaks 61 to 62, 62 to 63, 63 to 64, 64 to 65, 65 to 66, 66 to 67, 68, 69, 70, and 71. See this because, and you have the particular pattern of cross peaks in all of these things, and that is important. And the positive negative peaks which are there, this plays an important role with regard to the way you have the sequences in the polypeptide chain. So this plays a very extremely useful for as checkpoints. So if you don't hit the right kind of a peak pattern when you are in a particular sequential position, then you mean that okay, there is something wrong in your walk and so forth. By and large, it is very difficult to make a mistake in these ones, because they are so clear, the chemical shifts and the colors and or the signs are so clear that you are very rarely you can make a mistake. Unlike in the previous cases, if you are not able to make a continuous walk, you cannot be sure of what you have done. But here, even if you make a break in between somewhere, you can still start from some other point in your polypeptide chain and continue. So therefore, there is no ambiguity with regard to the selection of the particular place in your polypeptide in the spectrum. So this was extremely useful okay. So and that this we did. This was the FKB, and this was the sequential walk in the HNCN spectrum. HNCN spectrum, once again, there is you can walk through here. You can see from 35 to 36, 36 to 37, 37 to 38, 38 to 39, 39 to 40, 41, 42. See, you can walk through. I mean, here there is no difficulty in searching for the N15 planes because you already know where the N15 is. And you already know which plane you want to go in the three-dimensional spectrum. The three-dimensional spectrum, let me write that here again. The three-dimensional spectrum, if this is the HN proton, this is the N15 here, also N15 here, and this is the F1, and this is the F2, and this is F3. So you know exactly in F1, F3, which N15 plane he wants to go, because F1, F3 plane show you directly the N15 positions of I and I plus 1 in HNCN and I minus 1 and I plus 1 in HNN. Therefore, you directly go over there. And once you go into that plane, you also know which NH you have to choose because that is displayed in the F2, F3 plane. In the F2, F3 plane, you have the peaks. Let me just repeat that here. This is F3, F3, F1. Then you have two peaks here. This is in the case of HNCN. And correspondingly, in the F2, F3 plane, you have this one in, this one here. It's like that. So and this will be I and this will be I minus 1 and here it will be I and I plus 1. So you know exactly which plane to go, where to go. So therefore, and the NH proton chemical shifts are also known. In the case of HNN, you have all the three of them there. I minus 1, I plus 1, I minus 1, I plus 1, all the three will be there. So therefore, there is no difficulty in identifying, no scanning through. It is very easy, directly you will go there. And notice here, the glycine checkpoints here, G37, Q38, whenever there is a G37. So if you take this triplet, 36, 37, 38. So what happens, you see 37 is in the middle, okay? And if you take the triplet, 37, 38, 39, 37 is in the I minus 1 point there. So you see at those positions, you see distinct two positive peaks here, and the immediate next one, you have two negative peaks. I plus 1 position, you have two negative peaks, and G37 has a two. Everywhere else it is one positive, one negative, one positive, one negative. Therefore, this is an extremely useful checkpoint if you are walking through the polypeptide chain. Okay, so you cannot make mistake. So, and now those were when the glycines are there. Then we can create some other checkpoints by designing the pulse sequence in an appropriate manner, modifying the pulse sequence in a slightly different manner. The crucial thing to modify here is this particular pulse here. This is the so-called selective pulse. This is applied only onto the C alpha. Okay, so this pulse is applied, is a 180-degree pulse applied to the C alphas. Okay, sorry, C betas, not C alphas, applied to the C betas. And what is the purpose of that pulse? That pulse removes the C alpha, C beta coupling. Okay, when you apply a pulse selectively to only one of those, then as you have seen before in heteronuclear discussions, that coupling will be removed. So therefore, if you apply this selective pulse to the beta carbons of alanines, then the coupling to the alanines will be removed. Alanine beta, in the case of alanine, the coupling to the beta will be removed. If that is the case, then it will become like a glycine, because the glycine doesn't have a C beta. Therefore, if you can apply this pulse in the middle to the C beta of alanine, then you will remove the coupling, C alpha C beta coupling, then the alanine will become like glycine. You see that effect you can already see there straight away. The glycines will remain as glycine. Nothing happens to the glycines. Okay, glycine patterns will remain there. So you preserve the glycine patterns and you also get alanine patterns like the glycine patterns. This is typically indicated here. You see, for example, where there is alanine here, these alanines there. Typically in the HNN spectrum, alanine is positive and the two sequential ones are negative. What 10 and 12 are negative. Alanine is in the middle and the two sequential ones are negative. And if you see here, alanine HNN-A, which is the alanine modification, so it becomes like a glycine. A11 becomes negative, 10 is negative, and 12 becomes positive. The signs are interchanged. So this is the situation that will happen when there is a glycine. Therefore, alanine has become like a glycine. Another example here. So this is HNN. This is the particular 20, 21, 22. This is the triplet. 20, 21, 22 triplet, if you see, A21 is in the middle, this is positive, and the two sequential ones are negative. Okay, 21, 20, because this is like the normal three triplet without a glycine. But now, when I make this modification in the pulse sequence, see now this has become negative, negative, positive. That the middle has become negative, like it's like a glycine, and the one which is on the left becomes negative, and which is on the right becomes positive. This is like a typical glycine pattern when there is a glycine. Therefore, alanines are now behaving like glycines. You also have glycines and you also have alanine. Therefore, your number of checkpoints along your polypeptide chain increases quite dramatically. Okay, so this is a very important step, because you cannot make mistakes. Once you have this, you cannot make mistakes with regard to the assignments. You do the same thing for serines and threonines. Why? How serines, threonine? Okay, let me remind you of the carbon-13 chemical shifts. So these are the carbon-13 chemical shifts. This is the C-beta, alanine C-beta is here. This is very up. Okay, this is the general C-alpha area, and this is C-beta area, C-gamma area. But the alanine C-beta is very much up here. And the serine, threonine C-betas are here. Okay, they are mostly along with the C alphas, but they are distinct from the other C betas. So therefore, what you do is, you just as we did the trick for alanine, apply the selective pulse only to the A beta to decouple the C alpha beta. Now what you are doing here is, you do the same thing for the serine threonine. You excite all of these and eliminate all of these ones. That means you convert everybody else as glycine except serines and threonines. When you apply a pulse here, C alpha, serine, threonine, C beta will get applied. Okay, along with C alpha. But the pulse is not applied to the C betas of everything else. That means everything else becomes like a glycine. Now what you do is, you make a phase change of 180 degrees. After that, serine, threonine become like betas, and the other ones remain as they are. So here you have that kind of an idea, that you make the serines and threonines as glycines, and you have the glycines remain as they are. Okay, so that will. So therefore, you can see that here, this is the case when there is a HNN-ST. Okay, this experiment. So here what we are seeing, we are talking about the serines. The serines, here it is positive, negative, and see here negative, positive. Okay, D3, the one which is on the I+1 becomes positive, I-1 remains as negative. Okay, so this is the residue number. All of these are like that only. 9, 10, this is D3, E9, this is threonine here, T10, T10. Okay, and E9, T10. So these are all in the, and S49, L48. These are all overlapping. MM50 is also in the same area. Whenever there is something happens in the same area, because of the cancellation, the peak will actually get somewhat narrowed down. In fact, that you can use it to identify that, okay, such a thing is present here as well. In the normal HNN, you have this S49 as positive, and in HNN-ST, this 49 becomes negative. So that is like a glycine. Same is true with the threonine. So threonine, here it is positive, here it is negative. See, the correspondingly all the other patterns will also change. So they become like glycine. So therefore, in a polypeptide chain, you now, if you perform these two experiments, normal HNN, HNCN, and then you do HNN-A and do HNN-ST. These three experiments if you perform, then you have the entire, almost 70 to 80% your checkpoints. So therefore, it becomes extremely easy to obtain assignments. And this is the experimental sequence, as I mentioned. This is the HNCN-ST, that was the HNN-ST. You do a similar trick with the application of the pulse in the middle. Okay. So now, after this, what you can do is, you can take projections to make life simpler, even simpler, help you in analysis even better. Now you take projections. Projections meaning what? When you have a three-dimensional spectrum, you project the spectrum along one axis. Then you generate a two-dimensional spectrum when you take a projection. You can take projections on whichever one axis you want. If you take projection down the F1 axis, so this is F1 here, this is F3 here, this is F2 here. Then if you take projection down the F1 axis, you get the F2, F3 projection, right? You take a projection down 3, project everything onto the that one, you get a F2, F3 plane. Now, if you do that for an HNCN experiment, what you get like this. F2, F3 projection, you get a spectrum. Now, you see, you only have glycines and the ones which are after that. So unambiguously you fix where the glycines are and the residues which are next to them. Okay. Now if you take a F1, F3 plane, that means if you get a projection down the F2 axis, you get a projection up like this. This is the F2 axis. So, or down like this. Therefore, you have the F1, F3 plane. In the F1, F3 plane, you have all the HSQC peaks plus the sequential peaks. Plus the sequential peaks with every residue. Now, what is the meaning of taking a projection? It is not that you have to record a three-dimensional spectrum and then take a projection. Recording a projection means you don't increment that variable at all. You have three variables, T1 and T2, T3. T3 is anyway already recorded. T1 and T2. Suppose you record only one value of T1, T1 is equal to 0. Then that is equivalent to doing a projection down the F1 axis. You get only the F2, F3 plane. Similarly, if you give the T2 value is equal to 0, don't increment that in a three-dimensional kind of an experiment. Essentially do a two-dimensional experiment. Keep that as a constant value. Then recording a 2D spectrum, and then you can record a 2D spectrum in half an hour. Okay, so when you do that, so that is what is taking as a projection. So when you take a projection down the F2 axis, you get an F1, F3 plane. Here you see all the HSQC peaks plus the sequential peaks corresponding to them. Okay, so this is wonderful. So in this one spectrum, you can complete assignment you can get. If they are sufficiently well resolved as they are here in this particular case, you can completely assign the whole thing. So in half an hour, this is schematically indicated here. In the case of a G experiment here, this HNCN HG experiment here, you can walk through the polypeptide chain in the two-dimensional spectrum. There is a particular blow up here. See, this is G10 here. G10 has two positives. And immediately next to that, there are two negatives. This is what we saw in the case of HNCN previously. You have the two negatives there. So therefore, you can, all others are positive, negative, positive, negative, positive, positive, negative, negative, positive, negative, positive, negative. So therefore, you will find these connections in the two-dimensional experiment itself. So therefore, there can be no ambiguity over there. And of course, you might ask, how do you know that I should come here if there is something else? Because you have seen this in the F2, F3 plane. You know which nitrogen plane you want to go. Where the nitrogen is, the sequential nitrogen, you know exactly where it is. Therefore, you have to find a peak there, and you will find a peak there. So this becomes extremely useful. The projections play a very important role, and as a result of that, it simplifies your spectral analysis on one thing and reduces the experimental time on the other side. Now we can do the same thing here. The projections here, the first one I already showed you. This is the HNCN. HN suite of experiments, 2D projections here. And this is for the HNCN NHA. And this is just the nomenclature here, okay? HNC is the same as HNCN. The projections and their nomenclature, the experiments that describe, named differently as this. This is the alanine modification. This is the serine threonine modifications. In every case, you see the same residues plus the ones which are next to those. So the A28 you see, A46 you see, and you see G35, G10, G75. Okay, so G76, the ones which are next to that, you will see all of those G1s. And here also you see G70, and they have different signs, incidentally. You see also they have different signs. The ones which are sequential will have a different sign. Some peaks may not appear. If there is a complete cancellation of the intensity, then they may not appear. You may miss some things also. It is possible in some of those ones. Okay, so I think we had stopped here last time. And we now move forward to do further improvements in our technique. So this is the dual receiver. So far we were receiving the data on one channel. Proton channel we were receiving the data. So we have one receiver. Now when you design the pulse sequence, often you actually discard some of the spectra using Crusher gradients. Some of the magnetizations you use by using Crusher gradients. But that is also useful magnetization. Can we do that? Can we retain that and get useful information? Typically, for example, in an HNN spectrum, what is it? You transfer it from the amide proton to the nitrogen, label it, go to the, then you go through the C alpha and go to the next nitrogen, label it over there and go there. So this is a typical pathway for your HNN experiment. And when you're going through the C alpha, of course, you're going through the C alpha, we discard some data here, and then we go to the nitrogen again, then to the proton again, and then you collect the data here. And now in this experiment, what we are trying to do is, we don't want to discard this data. what do? We collect the data there itself. We acquire the data, and the magnetization here is on carbon, C alpha. So therefore, if you collect this carbon magnetization, and the rest of it you continue without throwing it, you detect it here and continue the process, and finally you detect the proton magnetization here as well. So as a result, what we have got? So we have here the T1, and this data which you get, we call is the T2 prime. Okay, this another time where we got T2, we collect the data here, and then we get the normal T2 and then the T3. Therefore, I will get here one two-dimensional spectrum and one three-dimensional spectrum using two receivers. This three-dimensional spectrum are the three variables, T3, T2, T1. For so far as this is concerned, I have two variables, T1 and T2 prime. Therefore, I have two variables. And what is present along the T2 prime? C alpha. So C alpha is present here, and on this one I have the N15. Of course, I have written here T2 prime because to identify with this, but this will be actually a frequency domain. In the frequency domain, there will be frequencies. So therefore, this will be 2D spectrum. This will be 2D spectrum and this will be 3D spectrum. The information is the same here. No, this is additional information we have got because we have not thrown away this data. We collected this. This requires two receivers. Of course, this was one of the things which it was not existing earlier in many places. This was first introduced by Ray Freeman. He was trying to do this. Then, of course, we adopted that one to introduce the second receiver, multiple receivers. In fact, when Ray Freeman had introduced it, it had not become sufficiently popular. Only one or two people had done. And now the Bruker, when they were not applied it to proteins, they had applied it to some other small molecules. And we wanted to apply it to the protein, and we told the Bruker we want another receiver. The Bruker fellows were confused. Okay, why do you want another receiver? Nobody buys a second receiver. Everybody does with one receiver. I said, you first give us. You first give us and we will show you what it can be done. And when we do this, see, you got such wonderful data. And now today, all spectrometers are sold with receiver on every channel. It is not one receiver. You have every channel you have a receiver. So therefore, multiple receivers has become a common feature. These are all called NEO systems. The NEO systems have receiver on every channel. Okay. Now, this is an details of the experiment which I schematically showed you earlier. The HNN experiment pulse sequence goes like this. C alpha detection happens here. Then we go back to the proton and proton detection happens here. This was the same thing which I mentioned to you earlier. You get a two-dimensional C alpha N15 correlation and a 3D H-N-N sequential correlation spectra, and you get these things. Okay, let me show you an example with regard to the experimental data. So this is the experimental data on some particular protein which was recorded. Now, what we have here, this is the C alpha nitrogen correlation. C alpha nitrogen, what is it you have? You have 45 ppm to 65 ppm or even less than that. And interestingly, you see in these correlations, the glycines which are distinctly above 45 ppm, because their chemical shift to the carbon axis is very distinct. All other chemical shifts of C alphas are above 50 ppm. 50 ppm and onwards, they go to 50 to 60, 65 ppm. Okay, but glycines are distinct, they are above 40. And as we've seen before, the glycines have a very special peak pattern. They are always negative, and see that here as well. The glycine peaks are negative, absolutely no ambiguity in identifying them. No ambiguity whatsoever. Now, therefore, all of these provide you a checkpoint or a starting point for sequential walk through the polypeptide chain. You can start from any one of those and you will find sequential connections. In this spectrum also, you have the sequential connections and the direct HSQC kind of a peaks. HSQC, but here it is carbon-13 and nitrogen correlation. And unlike in the HSQs, you have the proton and the nitrogen correlation. Here you have again a heteronuclear correlation, but this is the C alpha and nitrogen correlation. And here it is very distinct because of the N50 C alpha chemical shift of glycine. It is so distinct, you can find these correlations very well. I have drawn here such a kind of a correlation: 35 to 34, 34 to 33, 33 to 32. So you can go 32 to 31, 31 to 30, 30 to 29. Okay, so 29, where does it come here? Okay, 29 to 28. 29, it comes here. 29 to 28, 28 to 27, 27 to 26, 26 to 25. This is the 25. See, within this chain, you can walk along the polypeptide sequence in this on one spectrum. Earlier, we showed you in the case of the proton axis how you can do, but then of course, there the colors get mixed. And here there is no mixing of the colors. The colors are very distinct. Therefore, absolutely no difficulty in walking through. Same here. So there is a certain blow up, all the same spectrum, but here all the residues are annotated quite clearly. Everything is annotated. Here is only the few of those are annotated. So, and you can start from any one of those. You can start, we started from 35, you can also start from 47, you can start from 75, see 75 you can go here, and these ones also you can go like this. So in one spectrum you can obtain all the assignments. Okay, so next you can go a step further even, that there were in that dual receiver experiments, we got one 2D spectrum and one 3D spectrum. Now in this dual receiver experiment, you get two 3D experiments in the same. You start with the preparation, then you have the T1 evolution here. This is the schematic. T1 evolution, magnetization comes on a particular, this indicated here. You start with H alpha. From H alpha, you go to the C alpha. From C alpha, part of the magnetization goes to the nitrogens and part remains as it is, C alpha. So this is how you design the pulse sequence. So therefore, this is called as polarization sharing. Magnetization which is present here, it is shared between two pathways. One pathway goes here, other pathway comes here. Okay, now you can continue from here independently, continue from here independently. You have one mixing sequence here, another mixing sequence here, mixing 2 prime, mixing 2. So you have two pathways going in this direction. So therefore, you have one T2 prime here and T3 prime, T2, T3. And now that is what indicated here. The magnetization on C alpha is partly kept into C alpha I and partly goes into the nitrogen of I and I plus 1. And this continues as usual in the HNN spectrum. It goes to the nitrogen of I and I plus 1, amide of I and I plus 1, which is detected as T3. Now what remains here, what you do is you transfer this to carbonyl. This is C alpha I. What is present here is C alpha I. You transfer this to the carbonyl, because this is the one bond coupling, carbonyl, C alpha to C alpha carbonyl, and you detect carbonyl. This is the second receiver, because you make use of the second receiver here. This receiver detects the carbonyl, this receiver detects the amide protons. Okay, so this is proton detection and this is carbon detection, and here they detect the carbonyls. So therefore, as a consequence, you can immediately imagine what we should be getting here. You will get two 3D spectra. Along the F1 dimension, we have the H alpha. Here, F2 dimension, we have the F1 nitrogen I and I plus 1. F3 dimension, we will have amide proton of I and I plus 1. And what we will have here, F1 dimension will have H alpha, F2 dimension we will have the C alphas, and the F3 dimension we will have the carbonyl. All of these are of the same residue. Notice here H alpha I, C alpha I, C alpha I, COI. Okay, these belong to the same residue and these ones go sequential to I and I plus 1. Schematically, this spectrum is shown here. So you start from the H alpha, go to the C alpha, part of it is transferred here, and part of goes here, part remains there. And this one is then, what remains there is transferred to the carbonyl. You detect the carbonyl spectrum here. So this is the second receiver here, which is the carbonyl detection. And what goes here? It goes back to the amide proton, goes here as amide proton. Therefore, and then you detect the amide proton. This is the proton receiver. Here is the C carbon receiver. So this gives you your I and I minus 1 as in the case through the pulse sequence. So you get I and I minus 1. Okay, this is I and I plus 1, the passing will go through. If you are looking at the particular I, you get I and I minus 1, the two consecutive residues, 1 and 2 you will get. And this experiment is labeled as 3D HACANH. Here the C alpha is not detected. H alpha is detected, amide is detected, and nitrogen is detected. And here H alpha is detected, C alpha is detected, and carbonyl is detected. You see, label the C alpha here in this path. In this path, you label the C alpha also. Therefore, you have only one peak here, which is the I of particular residue. That is of the residue I. Okay, so this experiment is called as HACEOCO. So therefore, in one experiment, you collect this 2D data, two 3D experiments. What all assignments you get? H alpha I, HN I plus 1, nitrogen I plus 1, C alpha I, and COI. So these so almost entire backbone is covered in this one experiment. Of course, you didn't go into the side chain, you didn't go to the betas. You could also go to the beta. We have that experiment also, but I'm not going to discuss that here. But this is sufficient to indicate the philosophy and the principle, how you can do different kinds of designs of your experiments. So this is a whole lot of experiments here which have been designed as a consequence of all these manipulations. So this will give you an idea that, look, you can manipulate your pulse sequences in the way you want. The way information you want in your spectra, you can manipulate your pulse sequences. For that, you will have to understand the spin dynamics. That is why we spent sufficient effort in the previous set of lectures where we talked about the product operator formalism, how the various pulse sequences have to be analyzed, taking into account the transfer of magnetization pathways. And it's very easy to calculate all of these things, and many of these designs have been made by the students. So therefore, it is fairly straightforward, and you get extremely good spectra and very rapidly. Now you see, this is a whole lot of 2D and 3D experiments here, which I have listed. I just run through this some of these ones without going to the details of the thing, but because all the information is present here. What is a kind of a pulse sequence, or what is a kind of a transfer pathway, and what is the information that you get in each one of those? Okay, and these are of course the references for those papers there. Nobody who is interested, we can go through this because the data is there already. So you have 3D experiment, this we already discussed in great detail. 3D HNN-A also we have discussed. 3D HNN-ST. Now these are the projections which also we discussed. 2D HNC-NH checkpoints. Here you can get the checkpoints for the alanines, the serines, and threonines in the 2D projections. Now this is another modification which is called as best modification. This is relaxation enhanced. So that relaxation enhanced allows you to reduce the experimental time, and that is called as the best experiment. And this was initially introduced by somebody else. Paul Chandra from ETH has introduced this concept of best. This is the relaxation enhanced experiment, band selective enhancement of this thing that is called as the best. And then you get the sequential correlations as the same, but except that you can do experiment very rapidly. In a normal experiment, you give a relaxation delay of 1 to 1.5 seconds in the initial part, right? The D1 part, 1.115 seconds. And that is really the time consuming part. Now, if you can reduce this by using this consists of a series of selective pulses. When you do that, you can actually reduce that time to 300 to 400 milliseconds. So there is a substantial gain in the machine time. So you can record many spectra in the same experimental time. So you have this 3D best HNN, and this is the projection experiment once more. You get the checkpoints in alanines, the serines, the threonines, and following residues. Okay. And following residues. Why do I say following residues? You saw that if there is glycine, you have two positive peaks, and in the next residue, we'll have two negative peaks. Therefore, that is also a checkpoint. Therefore, immediately next residue has to follow that pattern. So therefore, all of these checkpoints you will get. Okay. So then you have the 3D HNN, 2D and CA. This is the result of a double detection, the dual receivers over there, and that is gives you two kinds, one 3D experiment and one 2D experiment, and this is using the dual receiver. And here you have, those were the HNN variants. Now you also have similarly the HNCN variants. HNCN variant, 3D HNCN we already talked about. 3D HNCN, this is the oh, this has come twice, is it? 3D HNCN, 3D HNCN, this has come twice. Okay. Now 3D HNCN-A, this is alanine modification. Then you can also have other kinds of modifications here. 3D HNCO-CNH. We will not go into the full detail. The magnetization transfer pathway is indicated here. In this one, you go from the amide to the nitrogen, nitrogen to the carbonyl, carbonyl to this C alpha, from this C alpha to this nitrogen, this C alpha to this nitrogen, then from nitrogen to this, and you detect it. So the bold letters here are the nuclei which are actually detected. Other ones are used for the pathway. for the transfer of magnetization pathway. So to distinguish which are in the pathway and which are in the detection, you label this as, make it bold. So CO bold means 3O is detected, and NH is bold, therefore H and N are detected. And in this particular version, you have the C alpha bold. So you detect the C alpha. You don't detect the carbonyl, although carbonyl is involved in the pulse sequence. NH to HN to nitrogen, nitrogen to carbonyl, carbonyl to C alpha, and C alpha to the nitrogen and to the nitrogen here, and you detect, transfer this here. See, carbonyl is used in the pathway, but you don't detect it. You detect the C alphas, the nitrogen, and the amide protons. So you have the glycines and the following residues as checkpoints. So this is the 3D experiment, and here you can have 3D NCONH, nitrogen, carbonyl, and proton. These three are detected. Okay, so therefore you see, you can design your pulse sequence depending upon what information you want in your spectra. So that simply significantly enhances your information content and allows you study various kinds of proteins very rapidly. And see that, you can see that here, this is of course a partial list here. This was prepared several years ago. The list is much more than this here. So you can study so many different proteins we studied in our lab using these methods. And this is intrinsically disordered proteins were not touched upon by other lots of people because of the difficulties involved in the chemical shift dispersion. But with this, whether it is folded, unfolded, aggregated, anything that is there, everything can be investigated using these methods. So therefore, what is the consequence of all of these? This is the summary of all of those ones. This is the unified NMR strategy for high throughput determination of backbone structures of amide protein, of small proteins. Small meanings up to 120, 130 residues, you can go fairly easily without much problem. And you use a whole lot of experiments here. All the experiments which you have to use are listed here. These are based on the 2D versions. 2D versions means projections. A projection experiment means you can record it in half an hour, each experiment. Therefore, if you have to record several of these experiments, you record in one day, you can record so many spectra. Okay, so Roman spectra you can record, and then you do a 3D HNCO nosy part, only record that also you can record very quickly. Backbone amide NOAs you can record. Now this spectral analysis is also pretty simple because of the checkpoints. So since you have the checkpoint, there is no search process, there is an operation, and this can be automated. Okay, all these spectral analysis can be automated. And therefore, we generated here an algorithm called as AUTOBA, automatic backbone assignment. And you can combine this, use these various data points here, and this spectral analysis can be done automatically. So it was our dream that as you get the data, you also get the assignments, because you can put the AUTOBA software on your spectrometer. So automatically it picks up the data and then it should do that. Of course, we didn't, before we could do that, I retired. And all the students who were there, they also ran away. They left. So, and incidentally, this AUTOBA software was written by an MTech student. She was not an NMR specialist, but a software specialist. She wrote a software to analyze all of these spectra in an automated manner. And so the consequence, you are able to obtain the structure of a small protein in 2 days. You compare that with what it used to take in 2 years in the very early days. Earlier it is only proton and OEs. It used to take 2 years. Here you can do in 2 days. Now there is a further development which has happened in the last 3-4 years, and all the spectra which are required for a backbone assignment can be obtained in 2 hours. And that is, of course, I'm not going to talk about that here. This is published, and that makes use of additional developments like BEST and also the non-uniform sampling. Non-uniform sampling reduces the experimental time much more. You can record a 3D experiment in 28 minutes. So one 3D in 28 minutes, one 3D in 22 minutes, and one 3D in 1 hour. So in 2 hours, you record the whole lot of data, and you can analyze that to obtain the structure of the molecule, because you can calculate the structure on the basis of the chemical shifts. I discussed that previously. You can use the Rosetta algorithm, okay, or CS2 3D. You can submit the chemical shifts, it will give you the structure. And that is an example here. So this is the structure which has been obtained in that manner. Okay, so I think we finished this here. So this file is finished, and now we go over to the next one.
Okay. Sorry,
Yeah.
labeling you are doing, na?
Yeah.
How do you know that homogeneity that
N15 labeling?
in 15 and carbon 13 there? You must
Because
be using this molecular recombinant technique, na?
Yeah, molecular recombination. See, you use 100% labeled ammonium chloride.
Acha, acha.
And ammonium chloride is fully labeled. So
Okay.
so is to carbon 13.
Okay, okay.
99.9% labeled carbon
Okay.
13.
Okay.
Therefore,
So
everything
no
that
chance
goes,
of-
no chance of anything else. So, okay. So now, so far, I will just give a brief introduction of what is going to come now. And then afterwards, we'll take a break. Okay. So so far we talked about how to determine the structures of proteins. We talked about the structures of nucleic acids, right? Now there is time to go back to fundamentals once more. The reason is you can use NMR to study the dynamics in the proteins. Okay, but before that actually made the ground to say that dynamics is intrinsic to NMR. You cannot live without dynamics in NMR. Dynamics is so crucial for, and so therefore it naturally comes out that you can study the dynamics of the individual proteins at various time scales. Okay, and the dynamics cannot be studied by X-ray crystallography. It can only provide you populations. Often people, crystallographers will tell you, I get a hazy electron density. Okay, but that is a population. That is not dynamics. That is a population. There is actually multiple conformations there, and you get a hazy distribution over there. Say, okay, there is a dynamic. Well, yes, it's different conformations, yes, but that doesn't give you the dynamics. Dynamic, when you say dynamics, we are determining the time scales of motions. What kind of time scales are there? So whether it is a microsecond time scale, millisecond time scale, nanosecond time scale, picosecond time scale, all these time scales we determine. The exchange contributions which are there, all of these things are intrinsic to the system. And these play very important role in functions of biological molecules. Many times I mentioned to you earlier, these intrinsically disordered proteins, they don't have a structure. Now you cannot crystallize this. But the intrinsically disordered proteins are extremely useful for functions of the functions inside the cell, because they can adopt a particular kind of a structure depending upon the binding partner. When a binding partner comes, it takes a certain structure. Therefore, you need to know the identifications of the dynamics in these intrinsically disordered proteins, how this dynamics changes, how the disorder changes, to understand the functions. A particular intrinsically disordered protein is able to perform several functions inside cells. Okay, and that varies depending upon the binding partner. Therefore, this cannot be studied by any other technique. This, and therefore dynamics is very crucial to understand. And dynamics of the proteins is intrinsic, and dynamics is intrinsic to NMR. And this is what we are going to show. Why do I say it is intrinsic to NMR? You cannot live without dynamics in NMR spectroscopy. So I think we will come to that. We'll take a small break here.
You can ask any doubt. You can ask your doubt. Ask your doubt. Or any doubt.
Yeah.
Any doubt? Yes. Right.
That's enough.
बोलती सारा पांच वास्ते बोले दी नहीं कोड़े बोली
Okay, so now, yeah, so now we are going back to the basics once more because this is where we have to see. Now all of you know that okay, you have a particular single spin. Spin is I is equal to half. You have two orientations there. There is a precision going around along the magnetic field. So you have m is equal to half and m is equal to minus half. So they precess in the anti-clockwise direction in this manner. So clockwise direction. So you have the RF, when you apply an RF along orthogonal axis, then you have absorption of energy from one state to the other state. And the two energy states which have, are indicated here, this is the alpha state, this is the alpha state, and this is the beta state, and they have different populations, and the population difference actually is determined by the energy, and the probability of the spin being in a particular state is given by this formula here, which is dependent on the energy, E alpha beta divided by KT. Okay, the ratio of the populations is of course determined by the delta E, energy difference between these two, delta E by KT. Okay, so this is the first fundamental, how the resonance absorption of energy occurs. When you supply the energy corresponding to this energy difference, there will be signal. Okay, absorption of energy will happen. Okay, now absorption of energy will slowly go to zero as the population start becoming equal. They because when you absorb energy, the higher level starts getting populated, the lower level start getting depleted. So at some stage, the two populations will become equal, right? We are continuously pumping in energy. When that happens, the rate of absorption of energy will go down, or the total energy absorbed will reach a saturation value. This is what this comes from the very first set of lectures. You have to go back and look at that. The absorption of energy rate goes down with the time because it reaches the saturation. Once the saturation happens, there will be no more absorption of energy. Therefore, that goes down. No more absorption means it is a plateau here. The energy value, if you see, there is an integral over there. It is a plateau. Absorption of energy will not happen. But we always see signal, right? No matter for how long you put the sample inside, you always see signal. What happens? How does it happen? What that means is there is a mechanism which is re-establishing the population difference. Okay, this when you supply energy, the RF causes the transition between the two states, but there is some other thing which is actually trying to re-establish the population difference. That is, restore the populations. What is that? And that is what we call as some kind of a relaxation phenomenon. And second issue is the following. So when you say you have the magnetic field applied here, magnetic field is this value, the energy of absorption happens at this frequency. If we change the energy of absorption, if we change the magnetic field, energy of absorption may happen at this frequency. So because depending upon the magnetic field, the energy separation will be different, and therefore the absorption of energy will be at a different frequency. But when it does so, the populations will also get readjusted because the energy difference increases, the probabilities and the populations of the two levels also will get adjusted. Now, what causes the readjustment of the populations? There has to be transitions. There have to be transitions to readjust. We know that RF is causing a transition. But what else is there? What causes the transition between the two levels so that they re-establish the population difference? What is the mechanism? Okay, so this is something which one has to understand, and that is where the crux of the NMR lies there. The populations will have to readjust as the field gets changed. What causes these transitions? There has to be an RF. You need an RF. Without the RF, how do you get the transition? And where does this RF come from? This RF has to be at different frequencies, at various different values. It must cause a transition at different values. Okay, and that is the fundamental problem, and that is called what is called as the lattice. There is a lattice. In addition to your spin system, there are so many other magnetic moments inside your lattice. In the solution, the water, or the rest of the other spin systems inside here, you have a lattice. And the lattice I represent here in this manner, and the spin is in this manner. Now the lattice has all kinds of energy levels. Lattice has all kinds of energy levels. And corresponding to your spin system, there is always this kind of energy level which is in the lattice. Therefore, if the energy is absorbed here, it will get released here. An upward transition is countered by a downward transition here. A downward transition here is countered by an upward transition there. These things can happen. So energy gained or lost by the spin is lost or gained by the lattice. So therefore, the lattice contributes to this re-establishment of the populations of the two. Once goes up, the lattice tries to bring it down. So lattice is the wide distribution of energy levels. Okay, now question is, how does this come about? How does this whole set of energy levels inside the lattice come about? And this is the dynamics here. Okay, now let's see how that happens. You consider this system. You have an ensemble, you have a particular magnetic moment here which is processing here like that. There are so many like that, so I put all of them here, various ones there. So many spins are there. This may be belonging to your own spin, or it may be belonging to some other spin. It may be belonging to the water, the solvent, or whatever that happens. Now, all of these are tiny magnets. Okay, the tiny magnets, they all have an interaction between themselves, right? So every tiny magnet produces a flux line around this. Okay, it has a flux line like this. So the flux line meaning what? It is a magnetic field. Flux line meaning it is a magnetic field line, magnetic flux field line. And if the spin is rotating in this cone, this whole flux line also rotates around it. The whole flux line also rotates along with that. Now, there are several of such ones there. So there is an interaction between this cone and this cone and this cone and this cone and this cone. All of these are fluctuating. Okay, now each of them has a flux line. Right? Therefore, each of these produces a magnetic field at this site. For example, if I take this, if I have a cone here, it will produce a magnetic field around that cone, in that cone. If I have a cone here, then it will produce, this field line will cause a field over there, changes the field over there. So therefore, every one of these ones influences every other one and produces a certain magnetic field flux line at the site of this nucleus. So therefore, every site what it sees is a superposition of the contributions of all of these. And since these are all rotating, these are fluctuating inside the solution, and they are also diffusing, the distance between the two also keeps changing. The flux that is produced will also depend upon the distance. The field that is produced by one magnetic moment at another magnetic moment is dependent on the distance between these two. This is by the dipolar coupling. And the dipolar coupling inversely proportional to the third power of the distance. Magnetic moment divided by r to the power q. So therefore, this distance is fluctuating because of the motions inside the cell. And the rotation also. Therefore, at every point, every magnetic moment sees a superposition which is fluctuating. I write here h of t. This is a fluctuating magnetic field at every site. So therefore, h of t is a sum of large number of RF fields, different amplitudes and frequencies. What are these RF fields? These are all created by this. They are fluctuating fields. H of t is the sum of all of these things. Now, how do we figure this out? If you have so many contributions here, so many fluctuating magnetic fields which are there, and each of these fluctuating fields is in principle capable of causing a transition. Okay, so now how do we analyze this kind of a superposition of thousands and millions of such kind of fields? How do we analyze this? This is done by what is called as Fourier analysis. Therefore, there is a Fourier relationship between the frequencies present and the field which is created here. And that is indicated here. Suppose I have two RF waves, the superposition of those ones will provide a time-dependent variation like this. If I have four RF waves, it produces a variation like this, time-dependent fluctuation. So in other words, the h of t is now a superposition of a large number of RF fields with the frequencies omega n. So an is the amplitude of the RF field and omega n is the frequency of the RF field. So you have all kinds of fields present there. Okay, the superposition of all of this function h of t is now represented as the sum of lot of these RF fields, an cosine omega n t. Okay, let me repeat. The fluctuating field, which I showed explained to you earlier, it fluctuates because of the translational motions, the diffusional motions, the rotational motions of all of the spin, the precessional motions. All of these will contribute a fluctuating magnetic field. The fluctuating magnetic field can now be. This is the function of time. Okay, fluctuating magnetic field is a function of time. Now, therefore, I can analyze this as a Fourier analysis in terms of frequencies. The frequency is a sum of a larger number of frequencies with the different amplitudes. That means this is an RF. This is an RF, right? A1 cosine omega 1t is one RF, A2 cosine omega 2t is another RF. So, so many different RFs which are created by the fluctuating magnetic fields. So, each element represents an RF with amplitude AN. And square of the amplitude is power. This we know. If I have the 2h1 cosine omega t, as we have indicated in the externally applied RF, that h1 square is the RF power, right? So in the same way, the AN square will be the RF power. The square of the amplitude is power. Okay. Now, so therefore, I write here the Fourier relationship in a continuous form. If I want to do, I write it in this manner. The frequency distribution in the resultant in coming inside this h of t is given by this Fourier relationship. I give a time minus t to t. Of course, you can take the limit as t tends to infinity. Now, this will be a complex function. This will be a complex function, and therefore if I take a time average of the, because it is fluctuating, this is fluctuating. So if I take a time average of all of these ones, the ensemble average, time average or ensemble average, this goes to 0. However, what I do is I take a complex conjugate of that and take a square, h stars t and htw. This is a positive number. This will not go to 0. This will not average to 0. Okay, and now I take the limit to t as of this factor. Now this is a function of frequency, and that is represented as j omega. This is called as the spectral density function. This represents the power at a particular frequency omega, because now it is square, right? This h of t will consist of the square of the amplitude, consists of the square of the amplitudes at every particular frequency. Therefore, since I take this, it means there is a square which I am already invoking. Therefore, j of omega represents the power at frequency omega. Now, question is, the fluctuations, are they random or is there any correlation between them? If h of t fluctuation is not random, has some correlations, then what does it mean? That what is the fluctuation at this particular time? What was it about a particular time before? Is there a relationship between them? Or what is it today now, and what will be after 1 microsecond or 10 nanoseconds after this? Will there be a relationship between them? Does it dictate that? That is a kind of a correlation. This is called a memory. It's called a memory. How much memory does it have? So therefore, it has some correlations. Then it will show up in the randomness, or it is a decrease the randomness of that one. And that is actually now in that, when you have that one, a detailed mathematical analysis will give you that the j of omega is given by this particular equation. This is the ensemble average of the h of t and this complex conjugate, and you have this parameter 2 tau c divided by 1 plus omega square tau c square, or a constant into tau c divided by 1 plus square omega square tau c square. Okay, at particular frequency omega, it is dependent on the correlation time. This is called as the correlation time. How much is the memory? How much is the correlation time? How much is the relationship between the fluctuations that are happening inside in the lattice? Okay, so tau c is called as the correlation time, which characterizes the molecular motions. Okay, and small tau c means fast motions. Okay, there is picoseconds or sub-picoseconds, the nanoseconds. Okay, this determines to what extent the memory lies, how much is the degree of correlation, to what extent the system remembers what it was about a picosecond before, what it was a nanosecond before. So that is the memory. So therefore, correlation time characterizes molecular motions. Small tau c means fast motions, large tau c means slow motions. So therefore, JW represents RF power distribution in the lattice as a function of frequency omega. This is called a spectral density function. Now, how does it look like? As I said, this is the transition probability here. This is the formula which comes from the first lectures. Okay, it's dependent on the h1 square. Is proportional to h1 square and gamma square t2 by t2. That is the exact formula there. But point is that it represents the proportional to the transition probability is proportional to the square. Therefore, the spectral density, which represents the square, is the power. Therefore, this represents the power here. Therefore, spectral density determines the probability of the transition, efficacy of the transition at any particular frequency. Okay. So, what is plotted here is you have depending upon the correlation time, how does the j omega look like? Okay, suppose your spectrometer frequency is omega naught and tau c is such that omega naught tau c is much larger than 1, then your spectral density function will be like in the black curve. Okay, this means omega naught is the same, but tau c is very large. Therefore, omega naught tau c is much larger than 1. And this represents large molecules. Why? Because the sluggish motions. Tau c is the large, meaning what? The motions are very sluggish. Okay, so therefore it is applicable to larger molecules. Small molecules, on the other hand, tumble very rapidly. So therefore, omega naught tau c is far less than 1. This represents the small molecules situation. In this situation, you see the power is distributed over a wide range of frequencies. J omega is uniform all through for such a large range of frequencies that dies on at 10. Okay. And for the intermediate case, omega naught tau c is equal to 1, it has to lie somewhere in between the two. These are two extremes. Omega naught tau c is much smaller than 1. Omega naught tau c is much larger than 1. These are two extremes. And the somewhere in between omega naught tau c approximately equal to 1, that will be an intermediate one. So this will happen like this here. So it will be the red curve which is like this. What is the consequence of this? What is the consequence? Because we said it is the transition probability which determines the efficacy of the transition, right? So therefore, that determines the relaxation time. How far the populations will re-establish. If the transitions are very efficient, the populations re-establish faster. So that determines the relaxation times. Therefore, obviously, this will have a connection to the relaxation times. Okay, let us look what happens. Suppose my omega naught is here. My spectrometer frequency is here. Okay. For a situation, suppose the molecule is such that omega naught tau c is much larger than 1. So how much is the power available to me? Only this much. Only this much. Therefore, relaxation will be very slow. Relaxation time will be very high. Now suppose I have the situation which is here. Now omega naught, take the other extreme, extremely small molecules. Omega naught tau c much larger than 1. The population the power that is available to you is this point. Is better than this. Okay. So more power is available to you. Therefore, the efficacy of transitions will be higher. But if I go to this situation, the efficacy is maximum here. The population is maximum. And the power available to you is maximum at this point. Therefore, you have the highest efficiency of transition when you have this situation. Omega naught tau c is approximately equal to 1. Right? Therefore, how does it depend? The tau c dictates what will be the efficacy of your transitions. Spin lattice relaxation time, therefore, the T1 depends upon what is your tau c. It should depend upon tau c. It should also depend upon omega naught. Correct? Because it is omega naught tau c which is important. It will also depend upon omega naught. It will also depend upon tau c. Okay? How does it show here? So if I plot here T1 with tau c, T1 has a minimum value when omega naught tau c is equal to 1. On either sides, it goes up. On either side, it is higher. Because we have seen earlier that in either side, on this side of the system, this is small molecules. Tau c is very small. On this side, it is large molecules. In either case, the efficacy of transition is less than what is at this point. Therefore, you have this kind of a V shape. You have a kind of a V shape for the T1 dependence on the tau c. And obviously, it will also depend upon the spectrometer frequency. So omega naught tau c is equal to 1 will be different for different frequencies. For 100 megahertz, if it is here, for 200 megahertz, it is here, that is at this point, 300 megahertz, it is here. The minimum has to occur at that point. Okay, the minimum this curve will occur at that point. Therefore, the T1 will be dependent on the spectrometer frequency and also on the on the correlation time. What kind of a molecule you will have? What is the kind of a motion you have in your molecule? See, therefore, automatically dynamics has crept in. Dynamics has come in form in two ways. First, you can have dynamics at the overall molecular level, or you can also have internal dynamics. In a large protein, you will have internal dynamics also. Apart from the total tumbling, you will also have segmental motions inside the proteins. So therefore, that will contribute additional dynamics inside that. So therefore, that is why I said dynamics is intrinsic to NMR, and this provides you a whole lot of information with regard to the dynamics in the proteins. Okay, now then we have the transverse relaxation. That was the T1. Transverse relaxation determines what is the loss of phase coherence between spins in the ensemble, also affected by tumbling motions. Okay, and this is reflected in the line weights and affected by chemical exchange processes as well. So all of these change the frequencies, the phase coherence between the spins where they are precessing in the transverse plane. So the loss of phase coherence is what is responsible for the T2. Okay, so when the T2 changes, the phase coherence changes, it will change the line weights, because the line weight is proportional to e to the minus T by T2 star. Okay, and therefore when the transverse relaxation is changed, the line weights will change. And line weights will change when there is chemical exchange process as well. This a particular proton exchanges between two sites which have different chemical shifts and the different line weight at different lifetimes, then you will have different efficacies. Okay, so now let's try and understand this. So you're considering two interacting spins. You have two interacting spins. You have the four energy levels: alpha, 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 beta, beta, alpha, beta, beta. And we have seen this before when we discussed about the NOEs, the same thing. Now here are the six. Now transition probabilities are there. Okay, before I say this, okay, now you see in this curve, if you see, if omega naught is here, 2 omega naught will be here. Okay, even that is 2 omega naught is like the double quantum frequency. This is a single quantum spectrometer frequency. 2 omega naught is twice that. So that means it's kind of a double quantum. Okay, and that is possible in small molecules. In small molecules, there is a power available there. So therefore, the lattice can actually produce a double quantum transition as well. It can cause single quantum transition. It can also cause double quantum transition. But in large molecules, it cannot. So there is no power available here at this point. But in small molecules, certainly it is. Therefore, depending upon the different kinds of transitions that I have listed, all the transitions here, there are single quantum transitions W1, 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 W1. These are single quantum transitions. You have W2, W0. Single quantum means one spin flip. W0, W2 are two spin flips. Okay, and all of these are produced by the lattice. They can be produced by the lattice. And therefore, I have possibilities of all of these here. Now, without going into the theoretical details of this, we have the formula here. The R1 is equal to 1 by T1. R1 is equal to 1 by T1. This is related to the correlation time in this particular way. This is for the homonuclear situation here. They have tau C. This represents the single quantum term. This represents the double quantum term. Both transitions do occur here in the case of R1. And in the R2, you have the single quantum transitions, double quantum transitions, and also at zero frequency, tau C. There's no frequency component here. This is also there. Then to that, you have to add here R exchange. R exchange is the contribution from the exchange that happens between two sides, and that contributes to the relaxation because it contributes to the line width changes, and therefore that is the R exchange contribution. This has to be added separately. So all of these will affect your relaxation measurements. Okay. Now if you look at for a particular kind of a situation, omega naught tau C far greater than 1, you can make approximations here. R1 will be proportional to 1 by tau C and R2 will be proportional to tau C. You can make approximations and see how that happens. And if this happens, approximately, the product of R1 and R2 will be independent. Okay, in the absence of R exchange. Therefore, you can use this trick to figure out if there is R exchange contributing in your protein or not. So if it is not a constant, then it means R exchange is contributing. If it were not present, this situation will be there. Okay, approximately. So you can give about plus minus 10% of variation, make a scope provision for that. But if anything which is larger than that, then it means there is R exchange code. You first detect the presence of R exchange in this manner. Okay, now this is the same slide which I have shown you here, which was, and this is the nanosecond time scale. Correlation times are indicated here. What is the time scales here? This goes from the picosecond to the sub microsecond time scale here. So 60 megahertz, the 360 megahertz. The T1 goes in this manner, but the T2 is monotonously decreasing. T2 doesn't show that kind of a V-shaped behavior. T2 is monotonously decreasing. Why? This is because of this tau c term here. Because of this tau c term, it is monotonously decreasing. It doesn't have that sort of a V shape. So therefore, as you increase the molecular size, T2 always decreases. So the R2s will always increase when you have large molecules. Whereas the R1s here, see here and here, actually both the T1s is similar. In the case of large molecule or small molecules, depending on the magnetic field you have this sort of a V-shaped behavior, where the T2 is monotonously decreasing with increasing one. Therefore, this is an extremely useful thing. On the one hand, it is useful, but on the other hand, it is also not useful because the lines become broader and broader. As you go to larger and larger molecular weight, you may not be able to see the lines, so there will be overlaps. And this is the reason for that. Okay, now we come to the chemical exchange there. Chemical exchange, how do the spectra change when you have chemical exchange? You consider two sites there, A and B. A particular proton exchanges between A and B, and they have two different chemical shifts. That is nu A and nu B. They are two different chemical shifts. What is the separation here? This is the simulation. This is the simulation here. What is the separation here? This is 1500 hertz to 3000 hertz here. So each one is approximately is it 500? 250?
250, I think.
Approximately to something like that. Yeah. So it is separation between them is about 250 hertz maybe. 250 or 500.
Nu and nu is 500 hertz.
500 I think. Yeah, about 500 hertz. And if the exchange rate between them is 10 hertz, you see the two lines are very sharp. Okay. Now the exchange rate between them is 100 hertz. Then you see start broadening. Broadening means the lines will become, intensity starts decreasing. And you go further, 500 hertz, so almost close to the baseline. This one here. They are still separate, but of course this middle point has become so close. Go to 1000 hertz is almost, it's called coalescence point. It's called coalescence point here. Okay, and you go to 2000 hertz, it starts sharpening once more. You go to beyond that, you start sharpening, further sharpening, becomes a single line there at the end, and that will be in the at the average chemical shift of the two. Here the two intensities are the same, therefore the populations of the two are the same, therefore it will be at the midpoint. This will be at the midpoint. If they were not at the identical populations, it will be at a weighted average. So therefore this is how the chemical exchange affects your spectral features. Okay, this is dynamics. This is dynamics in your molecule. And this is experimentally shown here for this particular case. So here it is the rotation, free rotation around this bond. So this is restricted rotation here, the free rotation there. The two CS3s are non-equivalent. So which position is seen? See, as you go, as you increase R2 intrinsic plus R exchange. So what is shown here, 400 megahertz of the aromatic proton. This is of the aromatic protons, not of the methyls. Aromatic protons in para-nitroso dimethyl aniline in the figure as a function of temperature. This is the temperature is increasing there. Run at 213, 243, 263, 283 and 303. So as a function of temperature, you see the changes in the spectra. Okay, these are aromatic position. These are aromatic signals. They are coming from these protons. Okay, so therefore you see at low temperature you have all the lines very clear, and as we increase the temperature the exchange rate increases compared to the chemical shift difference. Notice it is important that it is with respect to the chemical shift difference how much it is, and they start broadening. Further broadening here, the splitting is gone. then they see average chemical shift here, and then there is only one at this point which you see. This is further split because of the narrowing. So this is how these things will happen in the because of the chemical exchange. Okay, and the nuclear overhauser effect is also a similar thing. This is also a result of the dynamics, result of the relaxation, mediated with the dipole-dipolar interaction, which are modulated by molecular tumbling. Okay, the transfer of magnetization, you have the spin 1 and spin 2, their magnetizations are different, and therefore the I2Z, I1Z, these are different because their populations are different, and the populations are different here, therefore they have different magnitudes. Now, dipolar interaction can transfer populations from one to the other. This is what happens in the case of NOE. Whether you take carbon-13 and proton, you can transfer magnetization from the proton to the carbon-13 via NOE. You saturate the protons, the carbons will get enhanced. So this is what we have seen earlier, and this is exactly what is happening in the NOE. What mediates this? This is mediated by the spin lattice relaxation time, the dipolar interaction. Okay, therefore you see the relaxations plays a very crucial role in all of these things. Saturation of one signal affects the intensities of other signals, and this is because of the dipolar interaction transfer. Okay, now this we have seen earlier, so just a repetition of that. Large molecules, you have negative NOEs, small molecules, you have positive NOEs, and this is given by these equations. I don't want to repeat that here. Okay, so now we come to the protein dynamics, various kinds of proteins dynamics which are present there. What are the time scales of various kinds of motions? So you have the time scale all the way, you go from 10 to the power 3 to 10 to the minus 12. 10 to the minus 12 is picosecond motions, 10 to the minus 9 is nanosecond motions, 10 to the minus 6 is microsecond motions, milliseconds, seconds, and minutes. So you can have this kind of motions in your protein. All these kinds of motions are possible. What are those? You can see here bond librations, fast loop reorientation in nanosecond to picosecond time scale. Overall tumbling happens in the nanosecond to sub-microseconds here. Slow loop and side chain rotation reorientation happens all the way from here to here. Slow loop reorientation happens from the microsecond to the millisecond time scale. This is microsecond to millisecond time scale. Local unfolding, the protein unfolding. Protein unfolding can happen in millisecond time scale to the seconds time scale. This is the unfolding of the protein, the local unfolding. The global unfolding is slower than that one. So this can happen from seconds to minutes. Then chemical kinetics happens in this minutes to seconds time scales. Slow loop reorientation, this is again inside the protein structure in this scale. Fast loop reorientation happens here. Side chain also, the SS flipping, so these are, and then you have the aromatic ring flips. Aromatic ring flips, this happens minutes time scales. It can happen in that area. Now, how do we measure this? All different these kinds of motions which are there, which technique to use to measure which time scale motion. So if you are in this domain here, the sub-microsecond to picosecond time scale, then you use T1, T2, NOE. T1, T2, NOE are sensitive to these motions, you can measure this. And if you are in this time scale here, so microsecond to millisecond, this time scale, you can use T2 and the T1 row. T1 row is T1 in the rotating frame. You can use this one. You can also use the coupling constant. The coupling constants also get averaged out because every coupling constant is of the order of hertz. It's like per second, right? Per second. The 10 hertz is 10 per second. So therefore, it is of that order of magnitude. So you can measure the coupling constant. And then the chemical shift difference here. You can use the chemical shifts here and the coupling constant to measure this. Then you can also use hydrogen exchange. Hydrogen exchange meaning proton deuterium exchange. NH protons are exchanged to the deuterium. You put D2O, put the sample in D2O, then the D2O will exchange with the exchangeable amide proton. And you can monitor that exchange. And that happens in the slow time scale, seconds to minutes. Now, sometimes it can go to hours, it can go to years. PPTI, for example, has certain proteins which do not exchange even after 1 year. So there are some which are extremely stable, some which are extremely labile, and those which are on the surface of the protein are very labile. As you go in the interior, they become more protected. So things like that. Therefore, you can use hydrogen exchange to measure the slow dynamics. You can use T1, T2 NOEs to measure fast dynamics, and the intermediate ones also can be used for T2 and the coupling constants. And you can detect these various kinds of motions inside your protein. Okay, so the chemical exchange I have already shown you here, a particular kind of a situation there. How does it depend upon the chemical shift difference? Earlier I showed you the exchange rate dependence, how it goes. Now it is exchange rate alone is not the thing. Exchange rate vis-a-vis the chemical shift difference between the two. How much they are separated with respect to each other. So with regard to that, you have the various patterns appearing. So when this is a kind of a coalescence here, this is at that point, the exchange rate is approximately equal to delta nu 0 divided by root 2. Point delta nu 0 divided nu 0 is delta nu 0 is this separation. This separation divided by root 2. From this we can measure what is the exchange rate. Whenever you get this situation, when you do the temperature variation, at this point the exchange rate is given by this particular formula. And anything beyond that, you will have a fast exchange. Below that is intermediate exchange. It results in substantial line broadening and overlap of the peaks. Okay, and so this is the no exchange, slow exchange, intermediate exchange, coalescence, and fast exchange. So you can measure these at various conditions to determine your parameters. Okay, so this is a particular illustration here, relaxation data on a particular protein. And you can look at this in very carefully. See, substantial, this is the polypeptide with 160 amino acid residues. This is actually the work of one of the students in IIT Bombay, Amrita Bhattacharya. So this got published recently in 2022. This is a very important protein in your life cycle, and R1 is sensitive to nanosecond motions. We said because the T1s are dependent on is typically nanoseconds. The correlation times which you saw earlier, the nanosecond to 9 time scales. R2 is sensitive to nanosecond and microsecond to millisecond time scales. This you saw in the previous plot. Okay, and NOE is sensitive to the picosecond motions. The vibrations in the NH proton, NH vector, small orientations like this and this ones, this is dictated by the NOEs. Therefore, NOE dictates fast motions. Here what we are talking about? We are talking about non-proton-proton NOEs, heteronuclear NOEs. These are N15, these are N15 nuclei, N15 measurements here. Okay, this is the proton N15 NOE as a function of the sequence. This is the R2 by R1 ratio for the N15 lines. You check the HSQC spectrum. What you do is, you have in the HSQC spectrum, you have these various peaks. Okay, you measure the R2s, you measure the R1s for all of these peaks, and you plot this R2 by R1, and you plot the R2s here, and you plot the R1s here also. R2 by R1 is also sensitive to the R exchange because R2 contains the R exchange. Okay, so therefore here you have the R2s, you have the R1s, and you have the NOEs. Notice here, and this is the structure of the molecule. Helix, 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 loop, helix, and free C-terminal. So this is and the helix means the structure is more rigid here, obviously, and the loop areas have more flexibility. Therefore, you can see in the loop areas, these ones are higher, the R1s are higher. That means the T1 is small, right? Because of the faster motions. Faster motions contribute to low T1s and therefore high T1s, therefore the R1s will be high. Exchange contributions. Nanosecond time scale motions. Okay, now the R2s, if you see here, R2s are high in these loop areas. Seconds inverse. R2 high means T2 is low. Okay, so this is high molecular, and the chemical exchange contribution will also happen there. Apart from the intrinsic R2, plus there is R exchange contribution. Okay, so here you see these ones, R1s are very high in the case of loop areas, and in the structured areas, R1s are low. And you take the R2 by R1 ratio, same pattern appears as in the case of this. And heteronuclear NOEs, you see this the loop area, they are very, very small, very low. and the end points are actually even going negative. So most of these areas where there is a structured ones, heteronuclear NOE is approximately 0.7 to 0.8. But in the loop areas, this actually goes down substantially. So there is a segment-wise variation in the motions. Apart from the tumbling motions which you are talking about, there is a segment-wise variation in the polypeptide chain. So these are extremely important from the point of view of functions of molecules, which areas are functionally important. Now, if there is a loop which is flexible, then it actually becomes a scavenger, like a scavenger to bind some other target molecule. Ligand which is present, it will become a scavenger. It will go and it can go and figure out. It can bind anywhere. It can adopt the structure. So that is the benefit of the loops. Therefore, often we see the loops are involved in biological function. Okay, so now now how do we analyze this further? Quantitatively, how do we get more information about the various kinds of motions? Okay, we want to estimate the correlation times, we want to estimate the R exchange contributions, we want to do this in a systematic manner. So mathematically, this can be done by what is known as model-free analysis of protein dynamics. I have written once more this equations R1 and R2 for which was I had written earlier, but the same equations I have written once more. And this is for the homonuclear case. In the case of heteronuclear experiments, which is what mostly one uses for proteins and things like that, and that will be, it will be like this. For the heteronuclear case, the R1 is dependent on how many spectral densities. You have the spectral density at a frequency omega n. We are talking about nitrogen proton system, N15 labeled protein. N15 labeled protein, you have this is the d square is a constant which depends upon the gyromagnetic ratios, product of the gyromagnetic ratios, and then you have the spectral density at omega n, spectral density at double quantum frequency omega h plus omega n, and zero quantum frequency omega h minus omega n, and this is a contribution which is coming from the chemical shift anisotropy. C square j omega n. Chemical shift anisotropy also will be there, which will contribute to the relaxation. Dipolar interaction we talked about, which is the earlier equation showed. Dipolar interaction mediated relaxation was indicated. Now we have added here another relaxation mechanism, which is the chemical shift anisotropy mediated relaxation. For the R2, I have here zero frequency, J0, j omega n, omega h plus omega n, omega h minus omega n, and this chemical shift anisotropy. Okay, so and this again has dependence on the spectral density omega n and J0, and plus you add here R exchange. The NOE is dependent on omega h plus omega n and omega h minus omega n. This we are W0. You see, W2 is basically omega h plus omega n, and W0 is omega h minus omega n. So NOE will depend upon these two. There's the cross relaxation rate. The NOE is not affected by chemical shift anisotropy. It is dipolar mediated. Therefore, it is the omega 2 minus omega 0. That is a zero quantum transition, and omega 2 in omega 0 is zero quantum transition. Omega 2 is double quantum transition, and both things will contribute here. And those the transitions are indicated here for a two-spin system. Yeah, the omega n, omega n, omega h, omega h. So energy level is now drawn appropriately for representing a heteronuclear system. Okay, this energy separation is proton energy separation. This energy separation is nitrogen energy separation. Therefore, approximately they have to be placed in this manner. Okay, now for the model-free analysis, you modify your spectral density function in this manner. Why do we do it? Because you say there is also an internal motion in the molecule. Earlier spectral density what we considered was the tumbling motion. The tumbling motion alone, that was the correlation time tau c. But in large proteins, you not only have tumbling motions, you also have internal motions. That has to be accounted for. Lipari and Szabo made this modification initially. Okay, they described the spectral density function in this manner. There is a contribution coming from this overall motion, And there is another contribution coming from the internal motion. And that internal motion, therefore, you define by another correlation time, that is tau. Overall correlation time is given by tau c, and this s square and 1 minus s square dictate the order parameters. For the that represent how rigid is the system, and this represents how much is the non-rigid situation. So S square is the rigidity kind of a rigidity parameter, or the order parameter it is called, and 1 minus S square is obviously the flexibility parameter. Okay, so therefore for the internal motions you have this flexibility parameter coming in. For overall motion you have the rigidity parameter which is coming in. So you modify the spectral density function in this manner. So how many variables you have here? You have the tau c, you have the tau, and you have the S square. Okay, and then of course you substitute this in your equation for the relaxation parameters. Okay, now you measure this relaxation parameters. What do you measure? I already shown you the result here. What you do is you have this T1 T2 NOE data. Okay, T1 T2 ROE, I mean the heteronuclear NOE data, and you have this data here indicated. In this case, you fit this T1, T2 NOE data with the spectral density functions defined in that manner. Okay, and then you get this sort of a situation. For a particular protein of this type, you get S square is very low in this point, S square is very high, like 0.8 to 0.9. In this, that means this portion of the protein is very rigid. You can expect that because you see all helices, alpha 1, alpha 2, alpha, all of these are rigid features. Therefore, in these areas, the protein is very rigid. Accordingly, the S square parameter is quite high. This is determined on the basis of this data, T1, T2, NOE data which you have here, sequence wise, and you fit this with the spectral density function which I indicated to you earlier, which considers the S square parameter. Only with that S square parameter, you vary the S square parameter and try to fit it, then you will get this sort of a situation. And these red and the black, they indicate for two different frequencies. Okay, here is another example there. So you have now R1, R2 NOE data, which is what you collect. You collect the data on your protein. This is the protein which is about 130 residues, 30 residues long, and then you measure the NOEs. See, the NOEs are fairly low. In this area they are. So you look at, first of all, let us look at the chain. The chain is, you have the beta, alpha, beta 2, alpha 2, beta 3, alpha 3, beta 4, alpha 4, beta 5, alpha 5. So those are the ones which are the rigid areas. And in between you have the loops which are flexible. But it may not be that all the loops will be very flexible, because it depends upon which are the nearing structures, how the things are formed, how the protein structure is. Depends on the three-dimensional structure of the protein, because sometimes the loops are used to hold together two parts of the rigid structure, then they may not too flexible. So this can vary. Now you see the R1s here more or less uniform across all of it here, except at the ends. Except at the ends, they are, and then you see the R2s, there is quite a substantial variation here, and then this is very low. Here is a great increase, then compared to the average, and there is an increase here, average here, then it is quite a substantial decrease here. The NOEs, there is a quite, at the ends, this is very low, and then in the middle, where there is the big loop there, of course, there is a decrease there, then afterwards it's roughly the same, and small variations up and down. And now what you do is, you have these parameters, S square parameter, tau e, which is the internal correlation time, and then you also add R exchange. R exchange contributes to R2, right? So therefore, you fit your data here to these three parameters, S square, tau e, and R exchange. You may not have to use all of them at the same time. First use the S square. So this determines the various kinds of model-free models. Model 1, model 2, model 3, model 4, model 5, like that. What model 1 means, first you will vary only the S square, whether you can fit the data properly or not. If you cannot fit the data with a square variation alone, then you use tau e. And if you cannot fit that, then you use R exchange. So you can make combinations of all of these. A square tau e variation, a square R exchange variation, or tau e R exchange variation. You can make these variations, and then you see which residues have which contributions. So when you do that, you will see here a square is more or less constant in all of these areas except at the ends. And therefore, here there is great flexibility in the protein. Even though there are loops here, the variation is not too large in those except for some little bit down here. So it is not too large there. Okay, here it is substantially low. And then you look at the tau E, in these areas, there is a big contribution of tau E, internal correlation time. Internal correlation time, internal flexibility, that is quite high in these areas. If you look at R exchange, and you see there is a substantial contribution of R exchange in these areas. And this area, a few residues, so therefore exchanging between two conformations. What those conformations we don't know, but we just see here that R exchange is contributing to the relaxation parameters for these residues, not necessarily every residue. So that means there is a local fluctuations, local dynamics which is happening in these proteins, and that is what you are able to see by these different contributions of tau E and R exchange. Oops. Okay, now there is this is another example there, the R1, R2 heteronuclear, all the N15 data, remember, these are all N15s, N15 relaxation times, N15. We cannot do that in homonuclear proton case because there is no resolution. N15, you have to always use HSQC. You measure each of the HSQC peaks. And in this situation, this is the protein which one is investigating here. In all these loop areas, there is quite a substantial flexibility over there. You can see the R exchange contribution is maximum here. And which is that area? That is around the residue number 15. That is here. See, in the loop area, substantial R exchange contribution. That is reflected in the R2 by R1, and the order parameter is mostly similar except for a small decrease here in this area. There is order parameter is not changing very much. The protein is not very flexible, but R exchange contribution is happening. The local fluctuation which is happening, exchanging between two sides, and that is contributing to these ones. It can be ring flips, for example, here, and this is there is a binding here at this point there. And therefore, this is binding and releasing, that sort of things may be happening. Overall loop itself may not be too flexible. And you also have a large R exchange contribution at this point. This is at 35 residues. 35 residue is here, and this is the histidine is behind there. So in those areas, you are actually able to see exchange contribution in this. Okay, so therefore, you see how much the relaxation data gives you inputs into the dynamics of the protein system. Okay, now there is one other issue that comes in. You remember how many parameters, how unique are these numbers what you are getting? Are we sure that okay, you are getting correct results? How do we know? Why you are asking this question? Because the parameters what you are measuring is T1, T2, NOE. There are three parameters. And if you look and go back to my original equation here, how many spectral densities are there? There are 5 spectral densities. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4, and Z0. There are 5 spectral densities. 5 spectral densities are contributing to this. And you are substituting for these 5 spectral densities from the modified spectral density function which you are given there. Okay, but you only have 3 parameters. When you have 3 parameters, how can you determine 5 spectral densities unambiguously? Therefore, there can be an ambiguity. Therefore, your data may not be perfectly representing what is the variation in the spectral densities. Therefore, this becomes a question. Therefore, what you do, you make a simplification here. 5 spectral densities and 3 NMR observables, it cannot be unique. Therefore, what you do here is, since you are talking about proton and nitrogen, you can make certain approximations. You cannot do it everywhere. You can make certain approximations, and that is, you say omega h plus omega n, omega h minus omega n are not very different, and they are omega equal to omega h only. Because this is a 10 times difference here between the two. Therefore, you make an approximation that these two are equal to omega h, which means you are reduced 2 into 1. So that means you bring it down to 3 variables. When you do that, you can define your J0, J omega n and J omega h in this manner in terms of the relaxation parameters there. J0 is given related to R1, R2 and NOE, J omega N is related to R1 and RNOE, and J omega H is related to RNOE. So therefore, 3 parameters and 3 variables you have. Therefore, you can calculate these 3 spectral densities without any problem. So if you have that, then what is the data you get here? So you have this all the data which is there, R1, R2, NOE, R2 by R1 ratio, and then you have the spectral densities calculated on the basis of those data here. This is the 2 different magnetic fields, and therefore you have this black, and on one side you are using the dot points, and the other case you have the histograms. It doesn't matter. So you use the J0, J omega N, and J omega H. This will reflect upon what are the contributions in this. And J0 has major contribution from the slow timescale motions. Slow timescale motions are represented where? They are in large molecules. Okay, and they also, you see the exchange contributions much more in that one. And therefore that happens, and these are according to the magnetic field, they will go up and down. That is systematically according to that. Okay. After this, what you do, you have these things generated. You have an empirical relationship between J omega Hn and between J omega Hn and J0. By this empirical relation, this is purely empirical. Now you substitute this into this your equation, the spectral density function. You generate a cubic equation like this. Explicitly, you put the spectral density functions for these, for J0, J omega Hn, and you put this in equation, and you get, in terms of the correlation functions and the frequencies, you get a cubic equation like this. Okay, the cubic equation which contains the frequencies and the correlation times. So therefore, this will allow you to determine, by fitting your data, this will allow you to calculate the correlation times. So you can do this short range in the particular protein there. So you take the J omega H versus J omega 0. That is omega H versus omega 0. You plot this. When you plot that, the data, and you fit it using this equation, and you get this kinds of correlation times, alpha, beta, tau. You get these parameters, alpha, beta, tau. Okay, tau is what is relevant for us. Tau is the correlation time. See, when you do this, your particular kind of different kinds of fits you obtain there, you get a correlation times 1.86 nanoseconds in one case. Another fit, you got 3 correlation times there, 54.19, 0.81, 8.01 second. So at least 3 different correlation times are operative in this. And these are at 800 megahertz. Then you do the same thing for omega N versus omega 0. You get some other correlation times here, 0.18 nanosecond, 2.4 nanoseconds, you get here 3 nanoseconds. Okay. And similarly, you get different correlation times. So this will give you a distribution of correlation times in your protein. Okay, how much flexible it is, which region of the protein. Of course, this is not telling you which region of the protein is flexible. This is telling you what are the correlation times contributing, flexibilities. Region wise, you obtain from directly looking at the spectral density functions and the variations in the R1, R2 NOEs. But this is giving the quantitative numbers with regard to the correlation times. And you can, from these ones, you can calculate the R exchange contribution, which is related to the J0 at 2 different magnetic fields. You take, all these equations you have to assume, you take it for granted, okay? We are not going to derive these ones, but these are all well-established relationships. So you have the spectral density function at 0 frequency, at 800 megahertz and 600 megahertz. Then this is the relationship what we have in the denominator, and this gives you the R exchange at the frequency omega N. Okay, and that if you plot it here, you see a substantial variation in R exchange across the length of the chain, up and down, various exchange contributions. This must be expected because this data is in a situation, is a denatured protein. The protein is denatured in certain degree of guanidine hydrochloride, but the point is that there is a variation. It is not uniform all across. That means there are certain stretches of rigidity, certain stretches of flexibility, and accordingly you see different kinds of exchange contributions in this protein system. And that is what is demonstrated here schematically in a particular, all of this is in a particular protein denatured state of GD or GDPase effector domain protein. This is 130 residues protein. So you can see therefore in the ensemble you can represent all these kinds of dynamic situations. There are certain places where there is order, motions are less, exchange contributions are more, exchange contributions are less, which contain the turn and helical propensities at a few residues as in the proton NOE data is magnified to show the areas with high above average value R exchange marked red. So the red areas on where there is R exchange is very high, and the green ones are the ones where it is relatively low. Protein folding funnel is also shown to emphasize that these topologies belong to the denatured state. This is all here in this area. In this area, therefore, the denatured state on the top is not really fully denatured. There is a certain degree of order. The propensities are there for certain structures getting formed, and the exchange is happening between the folded and the unfolded state. The helical formed and denatured states, such as even in the 6 molar guanidine hydrochloride denatured state, you do have this. And these are important from the point of understanding protein structure and dynamics. I guess this is the last. So we stop here.
So that means that native state, the exchange is very slow.
Is low. In the native state of exchange is much less, except in the loop areas. In the loop areas, there will be more exchange.
Loop is actually quite loose there.
Yeah, quite loose. Yeah. Well, again, depends on the length of the loop. Suppose the loop is short and then it actually holds together two alpha helices or a beta sheet. Then the exchange may not be there too much.
So can you go to the PPS slide?
Yeah.
Lambda Hana. Use that equation.
This one?
The equation was there.
This one. Yeah.
Lambda, what is the D?
Oh, D is that constant. See, it depends.
D and C are
These are proportional to the chemical shift anisotropy contribution. C is related to chemical shift anisotropy. D is related from the dipolar coupling.
okay.
That gamma, it has this constant.
But where you will get those information from?
Oh, these are standard parameters.
Standard.
Standard. Gamma into gamma H into gamma N. That is what is it comes in the D, and NH vector distance. So this is 1.0 angstrom. So that is not different. And C is a parameter which can be measured.
Okay.
So this is the contribution C square into omega n. You saw that one, C square omega n in the relaxation expression, and that C is the same here.
Yeah.
And the D is that the D square appeared there also.
Yeah.
In that equation also D appeared.
Hello, Mahesh ji, आप किधर है?
किसी को कोई डाउट हो गया?
हाँ.
क्लोज कर लेना. ठीक है, इसको करेक्टेड है ना?
So now any question anybody has? So we are going to close now. If you have any doubts, we can very clarify that. What is that?
इतना ही भेजे न्यूक्लियर मैग्नेटिक रेजोनेंस.
Guru Krishna.
ये तो नया कुछ किया है.
So he is joining for another. He just joined. He has not put his year number, no? His registration is not done. All right, just copy it. Krishna.
Oh, also find out. Maybe some people will be interested for the imaging also, na?
There is also Rutisha Trivedi. What is it? She is also a new one.
Yeah, I think Rutisha also.
That is the registration number is there, registered. You should just try. Guru Krishna.
Please provide your registration number.
Okay. Please write your registration number in the chat box.
नहीं वो मिल जाएगी सर. वो ज्वाइन कर पाया मैं उसका है रजिस्टर. एक अपने पास